So students, welcome to lecture number 11, and up to lecture number 10, we have covered many topics, many guidelines regarding the design of singly reinforced beam. Now today's topic is deflection control requirements as well as developmental length. So these are the topics which we have already covered. That means design of RCC beam in flexure, effective span, what is effective span of beam, what are the requirements of concrete cover, spacing between reinforcement bars, minimum and maximum area of flexure reinforcement. So now it is very important part of this design aspect, that is the deflection control requirements. That means how to control the deflection and what are its effects of the deflection on the section, and what are the guidelines given by Indian Standard Code IS 456, as well as bond length, that bond strength, that means what is the bond strength, and that means how much strong is bond between concrete and steel, what are the main properties and what is the significance of this bond strength, and based on this bond strength we will be able to understand what is the meaning of development length of the bars in case of RCC beam section. So topic is deflection control, and as per clause 23.2 of IS 456 2000, and we will be going through the guidelines mentioned in the code in clause 23.2, that how code is recommending the deflection control, and that means how we can follow the guideline of the IS code regarding the serviceability criteria, that is deflection control, how the deflection can be controlled while we are designing any RCC singly reinforced section. And so far we have discussed that how we can prevent the failure of any concrete element due to ultimate limit state of flexure. And now the topic which we are going to discuss, this is a very important aspect of design of RCC structure element, and that is, here we have to ensure that whatever be the deflections occurring, or we can say what will be the maximum deflection which will occur when the beam is subjected to working loads. So that means we have to ensure that the deflection under working loads do not adversely affect the efficiency of the structure as well as appearance of the structure. So that means when there will be a beam, we can consider a beam is simply supported, or it may be a continuous beam, or it may be a cantilever beam. When it is subjected to loading, then due to the bending effect, there may be some deflection. And here we have to understand that how that deflection can be controlled, because we can't make it possible that deflection is zero. It may be micro type of deflection, and let us go through. Now, what is the excessive deflection? That means there may be a very micro level deflection which are accepted, but what are the excessive deflection that in beam or slab? Let us try to understand it. If there are excessive deflection, then ultimately they will lead to the excessive crack width. So that means crack width will be more when the beam will be subjected to the deflection, and ultimately it will your structure will lose the durability, and the bonding of water can happen in case of roof slabs. If the deflection is excessive, again it will ultimately destroy the structure, or you can say the durability of the structure will be at stake. And another important aspect we can say, that means if you are seeing excessive deflection, that means larger deflection in case of a slab or in case of a beam, then there will be a psychological discomfort to the occupant of the building. Those people who are living inside that building, and if they see that type of deflection in the slab, automatically, psychologically, they will be bearing a fear of collapse of structure. That means they will be just thinking that structure may collapse at any time. So if they have to stay inside that building, then they will be always in a fear of collapse of the structure. Now, how to control the deflection, and what are the codal guidelines, codal recommendations? So, deflection due to loads. Now you can see here there is a one diagram, and let us take it is a simply supported beam, RCC beam. You can see the reinforcement there. Okay. Now these are the supports. These are two supports, simple support, and this is a beam, RCC beam. You can say it is a concrete beam and reinforced with some steel. And we can consider that here this is the load on the beam. It may be live load. So beam will be having some self weight, that is dead load, as well as some live load, and ultimately when this load will be increasing, then this beam will be going to deflect like this. So we have to find out what will be the maximum deflection. So if the beam is a simply supported type, then definitely the maximum deflection will be at the middle. So this will be the maximum deflection. So this deflection will be due to the various type of loads on the beam. And in general, you have gone through the calculation part of various type of beams, and various type of loads may be occurring on the beam. And in structure analysis, you may have gone through how to calculate the deflection as well as slope and deflection. So that type of numerical you have already done, and from you may go through the various type of numericals, and you will be ultimately finding that this deflection in the beam, that means maximum deflection, it is directly related to the span of the beam as well as modulus of rigidity, that is flexural rigidity of the beam. So this deflection can be given by this formula, where k will be the constant. It may be 5 by 364 like that. So based on the various type of end conditions and various types of loads, you will be getting the formula for the maximum deflection. So my concern here is to illustrate that this deflection depends on the span. So that's why in the previous lectures we were more concerned to find out what is the effective span, that is we have to take into consideration while doing the calculation. Now another parameter is E and I. So L is the span length of the beam and EI is the flexure rigidity of the section. So now you can easily understand that if the span of beam is a constant, if a particular beam, and K is another constant, then this deflection in the beam is inversely proportional to the flexure rigidity of the section. And further, flexure rigidity, it is having two components, that is E and I, two parameters, where E is the modulus of elasticity of the material from which the beam is made up. That means if you increase the value of E, you can increase the value of E by taking another type of material which is having more value of modulus of elasticity. So deflection can be reduced. Or either you can increase, or you can take the sectional dimensions of the beam such that the value of I should be larger. So because moment of inertia of that section depends upon its sectional properties. So either you can change the material or you can change the dimensions of the cross section of the beam, and accordingly you can modify the flexure rigidity of the section. So that means if you increase the flexure rigidity, the deflection will automatically decrease. So putting all the values and going through various type of the formulas for the calculation of deflection, Ultimately, we can conclude that delta by L, that is ratio of the deflection to the span of the beam, is directly proportional to L by D ratio, where L is the length of the span as well as D is the depth of the beam, and it may be effective depth or overall depth. So it is very much clear, if L by D ratio can be controlled, yes, we can control it, because if this ratio you want to reduce the value of delta, then accordingly you can change the dimensions of the section. If L by D ratio can be controlled, then the deflection in a beam can also be controlled. So that's why code is restricting the value of L by D ratio, and that L by D ratio, according to IS code IS 456, you can just restrict the L by D value, and accordingly we can restrict or we can control the deflection. Now, how code is recommending, how IS 456 is recommending span by effective depth ratio, that means L by small d ratio. Now, the deflection of the structure or part thereof shall not adversely affect the appearance, as we have discussed earlier, or efficiency of the structure or finishes or partition. So accordingly, the IS 456 is limiting the value of the deflection in a way. In the first step, we can say the final deflection due to all loads. That means when the beam is subjected to loading, then what will be the final deflection? Final deflection due to all loads, which may include the effect of temperature creep and shrinkage. It should not exceed span by 250. So that means L by 250 final deflection. So deflection is just controlled by L by D ratio. Later on you will be going to find out the value. So code is suggesting here, or code you can say limiting the final deflection, that delta should not be greater than span length by 250. Why? Because here by limiting this we can control the crack width. The second point code is suggesting the deflection occurring after the construction of niches and partition, including all the other parameters, that is effect of temperature creep and shrinkage, it should not exceed span by 350 or 20 mm, whichever is less. So here code is suggesting, or code is limiting these two values: a final deflection due to all the loads as well as deflection occurring during the service life, that is during the construction of the niches and partition. So why this second condition? By providing this particular limit, this limit is provided to avoid any type of damage to partition as well as the finishes. That limit will be covered in the serviceability criteria. Now, when you refer clause number 23.2.1, where again span by effective depth ratio is mentioned, so what code is just giving you the guideline: the vertical deflection limit may generally be assumed to satisfy, provided that the span to depth ratio are not greater than the value obtained below. Here some values are mentioned by code. That means if during design you adopt this span by depth ratio, then it is the possibility, or you can say it is the maximum possibility, that your structure will be following all the guidelines and structure will be safe. So deflection shall be limited to the following. Now very first point is basic value of span by D. That means basic value of L by D ratio, and this is applicable up to span length up to 10 meter. That means if you are going to design a beam which is having a span length less than 10 meter, then you can adopt L by D ratio, that is span by effective depth ratio based on the support condition. If it is a cantilever beam having span length 10 meter, then L by D ratio you can take, that is equal to 7. So you can say L by D you will be taking equal to 7. So it is very much clear, because span length is already given in the numerical or in the design. So in the initial, when you want to just assume some effective depth of the section, then based on this criteria you can just assume the effective depth, that is L by 7. And if the beam which you are going to design, it is a simply supported, then L by D ratio can be taken as 20, and if it is a continuous, L by D ratio can be taken as 26. So from this very guideline, that is deflection control, it will help you in assuming the effective depth of the beam when you are going to design any rectangular beam based on the various type of the end condition. And if the span length is more than 10 meter, then it is very easy. You have to multiply. Suppose it is a simply supported beam of having span length 12 meter. Then what you have to do, you have to multiply this 20 by 10 oblique span. So 20 into 10 by span. Then it will give you the guideline, or you can assume the effective depth accordingly. Now another important aspect is this limiting value, that is span by D, can be obtained from these basic values. So earlier you have to calculate L by D ratio, that is we are going through these guidelines, so that will be termed as basic value of span by D. But these basic value need to be multiplied by modification factor. So we are considering two modification factor here. Now what are this? First modification factor, KT. It will depend upon area and the stress of the tensile steel. And this value KT you can get from figure number 4 in IS 456. So later on when we are going to design any beam section, we will be taking the value KT from that figure number 4, which will be based on the area of and stress of the tensile steel. That means how much is the tensile steel area you are going to provide, and what is the grade of the steel accordingly. Some information is given in figure number 4. So from that figure you have to get the value of KT. And another modification factor is KC, and its value depends upon the area of compression steel. So currently, because we are going to design singly reinforced section, so later on we will be going to design doubly reinforced section, in which we will be providing compression steel also. So when that compression steel criteria we have to meet, then we have to take the modification factor Kc, and that Kc value you can get from figure number 5. So you will get one modification factor value Kt and Kc, then multiply this L by D ratio which you got from earlier section, and multiply it with Kt and Kc, and accordingly you can assume as well as you can find out the deflection. Now very important aspect of the design. Earlier you may remember during the assumptions part, in case of limit state methodology, we have assumed that there will be a perfect bond between a reinforcement and a concrete, because if the bond between a reinforcement and a concrete is not effective, then this reinforcement and concrete will not be able to act like a composite section. So here are a few guidelines which we are going to discuss now. Now for concrete and embedded steel which we have inserted in the concrete, and both if they want to act as a composite section and to provide strain compatibility, then the force in the reinforcement steel need to be transferred to the concrete successfully. So that means they should be able to transfer stress to each other. That means when stress is coming on steel, then that stress will be taken care by concrete and steel as a composite section. So it is the bond which is responsible for the transfer of axial force from reinforcing bar to the surrounding concrete. So in other sense, we can say that this bond will be the possible. If there is some bond, effective bond, then only reinforcement bar as well as concrete will act as a composite section. And then if they act as a composite section, then only strain compatibility can be possible. And if this is possible, then we can apply the theory of bending to the section which we are going to design or which we are going to analyze. Now, if the bond is adequate, that means it is enough, then only the assumption taken. And you remember that one of the assumption was plane section before bending will remain plane after bending. So that assumption can only hold good when there is a perfect bond or sufficient bond between the steel and the concrete. If adequate bond between concrete and steel, this will result into, here we have to write that this is inadequate. If the inadequate bond is between concrete and steel, then it is the possibility that when a load is coming on the beam and some bending forces will be acting, then the steel will get slip out of the concrete. So slippage of steel bars can happen. So when if there is a weak bond between the steel and the concrete, then definitely they will not be acting as a composite section. So steel will be acting separately and concrete will be acting separately. So we will not be able to apply the theory of bending of limit state methodology. So it is very much required that a bond between concrete and steel should be efficient. Now the deformed bars. Earlier we were using plain steel bars. Now we are switched over to deformed bars. Now what are the deformed bars? These bars have rivet-like projection rolled onto it on their surface. Now these rivet portions on the steel bar will provide better bonding between the concrete and the steel. So that's why these deformed bars are more effective in taking the stresses as compared to plain steel bars. The bond stress between the concrete and the reinforcing steel will decidedly affect the size and spacing of the cracks in concrete. So now how much is the bond stress between concrete and the steel? It will directly affect the size as well as spacing of the cracks in the concrete. So based on these few points which we have discussed, you may be able to understand that the bond between the concrete and steel is very necessary or very important. Now let us go through these few diagrams. And very first diagram is there is a beam, RCC beam, which is still not loaded. So beam is before loading. So beam is staked as well as reinforcement bar is staked. Now when this beam is subjected to loading and some bending effect will be there. Now here it is the unrestrained slip between steel and concrete. You can see here when this beam is getting bending, then this steel bar will be subjected to tensile forces. And if there is not perfect bond between the concrete here and steel, then possibility of slippage of the steel will happen. Now in third figure, you can easily understand that here bond force is acting on the concrete. So when the force load is acting on the beam and it is subjected to bending, then some forces will be acting on the concrete. And this is the bond force acting on the concrete when there is a perfect bond. And similarly, these are the bond forces acting on the steel. They will act into opposite direction. So if there is perfect bond, then these stresses from concrete will be taken care by steel as well as stresses on the steel will be taken care by concrete. Now let us try to understand what is the meaning of the bond stress. So the stress developed at the interface between the steel and concrete. So that means this will be the interface here between the steel and the concrete. So when load is acting on, then some stresses will be developed between at the interface between the steel and concrete, and this is called bond stress. And it can be expressed in terms of the tangential force. This force is tangential force which is acting per unit nominal surface area of the reinforcing bar. So this will be the bond stress. Now, what is the bond strength? Now here you can understand the bond strength can be defined as the maximum bond force which can be registered by the steel bar. So when some load is acting, then what will happen? There will be some bending effect, some tensile forces will be acting, and this bar will be subjected to tension, as well as concrete will also be subjected to tension. But if the concrete, the tensile stresses which are occurring on the concrete, and if concrete is able to transfer these stresses to steel, so then possibility of cracks will be minimized. Now all these bond stress as well as bond strength depends upon the concrete strength, geometry of the reinforcing bars, that means whether bar are plain bars or whether bars are high strength steel bar, whether these are TMT bar, or earlier we have discussed that ribbed type of bars, and the structure member itself also. So what will be the bond between reinforcement and concrete? That will depends upon all these parameters. That means what is the grade of concrete, that means concrete strength, as well as size of the bar and the surface texture of the bar, as well as the member itself. Now from this diagram you can easily see that there is a connection is shown between beam as well as column. Now it may be a cantilever type of a beam, or it may be a fixed end of a type of beam. Now what we have to understand here, suppose it is a cantilever type of beam, then main steel bar which is taking tension, they will be provided at the top, and these rings are the shear rings which we have already discussed in the previous sections. So column is there. Now we have to understand another topic, that is development length. So development length, what is exactly? Now based on this bond strength which we have already discussed, it is required to extend the length of steel bar in concrete. That means we have to extend the steel bar into the support, whether it is a column support, whether it is any type of support which is we are going to design, so that to develop enough bond strength, so that steel must be able to take the tensile stresses from the concrete without slipping. So let us consider, suppose this is the section which we are going to consider. Now at this section you can find out what is the stress at the steel level. So then beyond this particular section you have to extend the steel bar, and what is the length of steel bar into the support, and from the face of the column or face of the support, it will be termed as development length. It is required to take care of all the stresses. So that's why code is guiding some development length criteria. So what this is the information given in code. What code is suggesting, the calculated tension or compression. That means when you are going to calculate what is the compressive force in the steel or tensile force in the steel based on the singly reinforced or doubly reinforced section, at any section shall be developed on each side of section by an appropriate development length on end anchorage or by a combination. So sometimes we call this development length and end anchorage, they are same thing. And if we are provided some anchorage, later on we will be, when we are going to design any numerical problem, any design of RCC beam, then we will be going into detail about the calculations and what is the anchorage which is required. Now what is development length? So as per clause 26.2.1, we can do the calculation. So we have to find what is the this extra steel required to be inserted into the support, so that this main steel can be able to take the stresses. Now, from IS 456 clause 26.2.1, we can calculate effect development length by this particular formula, where LD is the development length required, and the phi is the nominal diameter of the bar, which you are, if this is 20 mm die bar, then phi will be 20 mm. And the sigma S is the stress in the bar at the section considered at a design load. So later on we will be able to understand all the information more clearly. Now tau Vd is the design bond stress, which we have already discussed in the earlier section, that what is the bond strength, what is the bond stress. So tau Vd is the design bond stress, and that information is given in a table, that is 26.2.1.1 clause when you refer. So this is the table which is mentioned there in the code. So based on the grade of concrete, we can find out the design bond strength, that is design bond stress tau Bd you can get. Now this is the design bond stress in limit state for plain bars. If you are using plain bars, then you can get this value. That means if you are providing plain bars of 20 mm dia in suppose M20 grade of concrete, then tau Bd value will be 1.2. So this tau Bd value will be 1.2, and this phi will be 20 mm dia, and sigma s will be the strength of the that steel at particular section. Now if you are using the deformed bars, generally now we are not using plain steel bars, but we are using deformed bar. And if it deformed bar is confirming the guidelines given in IS 1786, that means specification what are given in IS 786, then this value given in table, suppose we are considering M20 grade, and for plain steel bar it is tau Vd is 1.2, but if it is the you are using the deformed bars, then you can just increase the tau Bd value by 60%. That means you can multiply 1.2 by 1.6, and then you will be able to put the value here, and accordingly you will find what is the development length required. And if the bars are in compression, then the value of bond stress for bar in tension shall be increased by 25%. So based on this information which we have discussed today, we can calculate the development length which is required, so that we are able to understand that how much steel length is required to be inserted into support. Thank you.